I'm Jan Oliveringat, and this is joint work with Sayed Wakivali, and it's about semantic comparisons of Alloy modules, of Alloy models. So Alloy models are shown here. One example is shown here on the left. Alloy is a textual modeling language based on first-order relational logic. And there are some language elements, for example, signatures. They're a bit like maybe classes and class diagrams. They can be abstract. We have inheritance between signatures. We have fields in signatures that describe relations between signatures. And then we have multiplicities, so set or one. Then we have facts, like down here, we can have functions, predicates, and also commands and assertions. So down here, we see an example command, which runs, which tries to find specific instances that have this form where the number of requests are greater than 3 for a scope of 4. And Alloy is used a lot for design exploration, but also for verification of software designs. And in the models community, it's also been used as a background solver for other analysis problems. So it's quite a popular language. And now the question is, why would we want to compare Alloy models? Here is an example where a team has developed a model about endpoints, requests, and login requests. It's a simplification of an existing security analysis of an internet protocol. And here we see that requests, they go to some endpoint. And login requests are special requests, and they come also from exactly one endpoint. And now the team is exploring this initial model that they had, and they find this example instance. So the Alloy analyzer can compute instances for us, and this team found this instance and doesn't really like it. So it conforms to the model, but the team sees that, well, there are login requests that basically go nowhere, and that's not so good. And they also are from the same endpoint, and the team doesn't like that. They think that at any point in time, every endpoint should only have one login request. So they create a new version of the model, this one. And there are some quite obvious syntactic changes. So we see here that an inline fact has been added where we set for login requests, we set the targets to exactly 1. And then there is another fact that says that this from is injective. So for all 2 login requests that we have, if they have the same source, then this means that they are the same request. And then another team member has developed this model, which looks much shorter. And we see there are very different changes here. So the signature request, the abstract signature, has been deleted, and the field 2 has been pulled down into the only kind of sub signature. So now it's all in the login request. And then this fact here is a bit more fancy way of restricting the relation from to exactly these multiplicities between login request and endpoint. And now the big question is, first, maybe let's look at some instances that are common to this model, to these 2 new models, and check whether they're good. So the team looks at this instance, and yeah, it looks very nice. It doesn't have the problems of the previous one. Every login request has a target, and every endpoint only has one open login request. So that's nice. Now, the question is, are these really, on a more higher level, are they refinements? So did they only remove instances? And we can now use semantic comparisons to check whether they are refinements. We could then also maybe want to compare the 2 competing versions here and check whether they have maybe equal semantics. So we could check the equality in terms of semantics. So the semantics here would be the set of instances that they can generate. And then if we look at maybe the semantic difference, we would see that this instance here on the left is really an instance that has been removed in both of the new models, and they actually have equal semantics. Okay, now what we mean by these semantic comparisons, a little bit notation. So first, the Alloy analyzer provides a way of analyzing Alloy models in a bounded scope. And the semantics that we talk about here, they are all in this bounded scope. So every semantics that you see, that's the bounded scope. So this is what Alloy would compute. And here we use this semantic notation. So if we execute a specific command in a model M, then the resulting semantics is a set of instances, and instances are a set of atoms and relations in Alloy. And then we can write down some interesting comparisons. So for example, the semantic difference, we might be interested in what are the models that were added in the semantics of, what are the instances that were added in the semantics of model 2 that didn't exist in the first model. Or we want to check refinement or extension or simply the equality of the semantics. And how do we solve this? So intuitively, if we go and try to enumerate all the instances, this might be quite a bad idea and maybe infeasible. So what we decided to try is we tried to merge the two models into a single Alloy model, where we have that the single new Alloy model would contain the semantics of both of the input models. So what we would then only have to do is to find constraints where we can restrict this new merged model so that the semantics of the new merged model are exactly the same as the semantics of either of the starting models. And then by some Boolean combinations over these constraints, C1 and C2, we can express all these analyses that we described on the previous slide, and we can compute witnesses or examples that demonstrate this semantic relation. So for example, we can compute witnesses for semantic differencing, or we could compute counterexamples for equivalent semantics. And now, in a high level, a merge of the two first model variants from the previous example would look like this. And these are the, here, these predicates, they would be the C1 and the C2. But now we'll go step by step of how we would get this merged model. So we will look at signatures first. We need to merge, of course, signatures that have the same name, so that are common to both models, but they might have different attributes or different multiplicities. So what we need to do to express the semantics of the signatures in either model is we have to find a least upper bound in the multiplicities, for example. So now here we look only at the multiplicities. So we need to find the least upper bound of the multiplicities, and the multiplicities in Alloy for fields and signatures, they can be the ones here on the right. And in this example, if we would have in model 1 a singleton signature and in model 2 lone, which is 0 or 1, then the least upper bound of this would be lone. And then the merged model would have the least upper bound lone for the signature of with the name request. Now, if we have a signature which is unique, so it's only in one of the models, then we do a very similar thing, but we take the least upper bound of the original multiplicity and multiplicity no. So here, the least upper bound of 1 and no, that's simply lone. So then we would have lone here. And this is the reason for this is we want the model, the merged model, to be able to express basically the semantics of the original models. And then it gets a bit more complicated because the common signature could have common fields. And then fields, they also declare a type and a multiplicity. So then the idea is, again, we use the least upper bound to represent both. And the least upper bound of two disjoint types, this would be in Alloy their union. And the nice thing is that Alloy is powerful enough to express these union types in expressions of field declarations. So this is how we merge it. We take, again, the least upper bound of the multiplicity, sum and lone. This would be set. Because sum means at least one, so the only common thing above them would be set. And then the union of the two signatures. Now, or the two types. Now, for unique fields, what we would do is we would again take the least upper bound of the multiplicity with no. And this also works for fields of higher arity. So that's possible in Alloy. It gets a little bit more complicated, but that's described in the paper. And some other more tricky parts in the translation, they're actually the inheritance. So Alloy has two kinds of signatures. Alloy has type signatures. That's the ones we saw so far. And it has subset signatures. They are a bit more tricky. And both of them have an inheritance mechanism, and both of them can actually be mixed in terms of their inheritance. So that's a bit more tricky. That's in the paper. Then we can have references to signatures and other fields in field declarations. And then it's very important that we take care of scopes and things like that. And other things that are in Alloy models are facts, signature facts, functions, predicate. So all of this, we describe how to do it in the paper, and it gets a little bit more complicated then. But one important thing that we need to create also are these two constraints to get back to the original semantics so that we can express things like semantic difference or semantic equality. So these things that we need to pick up on the way, they are the predicates C1 and C2 to express the semantics of model 1 and model 2 in the new model. So in this example, if we transform this field where we had some request to a set of request and login, then we add a constraint that the relation that we describe with this field is restricted to the relation that it was in the semantics it had in the previous model. So here what we need to do is we need to actually look how can we express the structural parts that Alloy structurally expresses, how can we express them as constraints. And then there are another thing would be the scopes. So Alloy has quite a few implicit scope restrictions. For example, in the case of inheritance, the scope is a bound on the number of instances that each signature can, or a number of atoms that each signature can create. But here we simply use the Alloy analyzer on the original models to compute the scope. Then we introduce multiplicity restrictions using integers. And then again, for the scope in the combined model, we take the least upper bound, which in that case is simply the maximum of the original scopes. And then we would compute also the required bit width to restrict these, to express these constraints. So we have implemented this on top of the latest Alloy version. And the way we did it is we implemented it as merging based on Alloy's abstract syntax. So we used Alloy's parser, Alloy's abstract syntax representation, all of it native Alloy APIs, and the algorithms are mostly in the paper, but also the Java implementations are directly available on this GitHub page. There is a small warning here, so that we integrated an extension of Alloy's graphical user interface, but that uses a default scope. So the API that we also used for evaluation is a bit more powerful. So if you really want to use more than the default scope, then you need to use the API, or we need to extend the graphical user interface. There are some interesting limitations. So Alloy supports some higher order quantification, but not its negation. In this case, our comparison might fail because the comparison might require negation. Then Alloy has an internal ordering predicate, and you can't treat it as a normal predicate. So this just doesn't work, and there are warnings in the code also. Then fields of different arity, we can't support this, and signatures of different types, we also can't support this. We evaluated our work in terms of what is the cost for the semantic comparison and what is the impact on the limitations of the translation. So we used some data sets, for example, all the models that were available on the GitHub of Alloy and in the Alloy book, and then 2 benchmarks from recent works on incremental Alloy analysis. And here are some results. So we evaluated the semantic difference comparison in both directions on all the consecutive model pairs. So, and what we represent here is the overhead, basically the ratio of analyzing the compared model, the combined model, divided by analyzing the individual models. And we looked at the subproblem size and the solving time. And you see that the numbers here, the medians, so for 50% or more of the, or less of the specifications, it's actually quite good. We only have this kind of overhead of factor 2, but you see that the maximum values, they might go up quite a bit. But the scopes that we use here, if you know Alloy, so scope 18 is already quite big for Alloy for complex specifications. And we had some timeouts, but actually more timeouts on individual models than on the combined models. And the maximum memory we used was up to 4 GB, so that's probably also still fine. The limitations, well, they mainly came about this ordering predicate. So other things are not really happening, not really used in the data sets that we had. And the ordering predicate also was mainly in the collection from the alloy master branch. And the ones in alloy, in iAlloy in the benchmark, they're actually copies of the ones from the master branch or modifications of them. So it's basically coming down to the same specifications that use the ordering. So this would be a thing that we might have to look into how to support this. And as a conclusion, so we now have a way of semantically comparing alloy models, and the input and output, that's actually the same as alloy would compute for the individual models. So the instances that you get, they are compatible exactly with your original models. And we compute these comparisons via a reduction to alloy, where we merge it into a single model, and then we can evaluate these model semantics, basically using the constraints that we collect on the way. We have probably an acceptable overhead on complex models and even with quite high scopes. Now, the next steps would be to maybe even avoid this generic model. If you want to really go for performance improvements, you might look at what these incremental analysis tools are doing. And another thing would be to maybe improve the understanding of the comparison results with the witnesses and examples in a maybe nicer way.
All right, thank you so much. We have, first of all, I'm asking everybody in the audience to please put your questions in the chat. There is already a question from Martin, which I'm going to begin by reading. And the question is, are you aware of limitations in your approach in order to apply it to UML OCL models?
Yeah, that's a good question. I thought about this today as well. So I think that so one thing we're doing with inheritance is that we're flattening it, and alloy doesn't have multiple inheritance. So there are of course some differences between the meta models of alloy and those of, let's say, class diagrams in UML. So I guess that this might be an issue where our flattening or translation might not work. But yeah, we would have to look at the details, and I guess it would come down to some special features in the languages. So we were quite happy that it works for the alloy language.
All right. The second question actually corresponds to my question as well, from Usama Ben Jair, maybe. How could you make sure that your interpretation, refinement, semantic equality is valid out of the defined scope? So my question is a little interpretation of this, but let's hear the answer to this one, and then I'm going to ask mine.
Okay, so first, just to clarify, we are not making sure of this. So what we are making sure is that the scopes that you defined in your models, that this is what we analyze against. Now, if you wanted to make sure of this, then you're maybe asking very similar questions to, let's say, is an alloy model, does it have instances that we just can't find because our scope is too small? So there are some works that look at subsets of the alloy language where you can answer questions with ignoring a scope. So for ignoring a scope, I think that only works for a subset of alloy. But yeah, what we did is we basically simulate the scopes that you gave in your initial models.
Okay. And my question is related to monotonicity with respect to the scopes. So if I have a witness to non-equivalence up to the scope n, will this witness to non-equivalence work in the scope n+1?
So in
or
our
does
work,
it mean that yes, provided that certain funny language constructs are not in the model?
I mean, an easy way to do this is you can just have a very, very simple model with one signature, and in one version you restrict it to scope 5, in the other one you restrict it to scope 6, and then 6 instances are a witness for non-equivalence, right? So basically in this case, you can just always do that. So if we take the scope into account, you can always, you're always limited with the scope. So yeah, even already with with single signature models.
All right. Thank you. Any last minute questions? Okay, well, I have one more. Besides performance tests, did you perform other tests to detect potential errors in your approach?
Yeah. So basically what we did is we calculate these instances, and then we create, we basically check the instances so we ran semantic difference in both directions. And then the instances that we found as the semantic difference, we try to check whether they are really instances in the model that they are supposed to be in. So basically, this checks our merged model to check that we don't make any mistakes. So if we can really find that instance in the original model, then there's some good indication that our merged model is not too bad.